Hello everyone, welcome to our channel Mathematics Pathshala. This is a problem of CSIR Net September 2022 Mathematical Sciences. The question ID is 396. This is a problem of Abstract Algebra Part C. See the question first. Let A equal to a ring, a quotient ring ZX by the ideal generated by these two polynomials. Then which of the following statements are true? A is an integral domain, A is a finite ring, A is a field, A is a product of two rings. So first, let me study about this ring. First, about this ideal generated by these two polynomials and then this quotient ring. So see first, let us suppose this ideal denoted by I, which is generated by these two polynomials x square plus x plus 1 and x cube plus 2x square plus 2x plus 6 in zx. See first, so any element of this ideal is of the form some this x square plus x plus 1 into some polynomial say phi x belongs to zx, and this polynomial x cube plus 2x square plus 2x plus 6 into another polynomial say psi x from zx. So any element of this ideal is of the form like this. This is the structure of all this ideal. All the elements of this ideal are of the form this. So now clearly if we take here psi x equal to 1 and phi x equal to minus x, then we get x cube plus 2x square plus 2x plus 6 into 1 plus minus 1 into this polynomial phi x equal to minus 1, so sorry minus x, so x into this x square plus x plus 1, this belongs to I, and this is actually our x square plus x plus 6, this belongs to I. Now also, since this belongs to I and also x square plus x plus 1 belongs to I, so x square plus x plus 6 minus of this x square plus x plus 1, this also belongs to I, and which is actually our 5. So 5 belongs to I. Now see, this 5 belongs to I as well as this x square plus x plus 1, this belongs to I. So this we have that ideal generated by 5 comma x square plus x plus 1 is actually subset of I. So now, and also see 1 does not belong to I. Just verify this. So this is very easy to check, because if we suppose 1 equal to of the form this x square plus x plus 1 into phi x plus x cube plus 2x square plus 2x plus 6 into psi x, then we can find this phi x and psi x such phi and psi does not exist. So 1 does not belong to I. So I is the proper ideal and also containing this ideal. We name it by J. So J is subset of I. Now consider this ring, this quotient ring Zx by this J, that is 5 comma x square plus x plus 1. This quotient ring is isomorphic to the quotient ring Z5x by the ideal generated by this polynomial x square plus x plus 1. This theorem actually we have proved in one of our video in abstract algebra. So Just see this result from there. So now see here, this polynomial x square plus x plus 1, this polynomial x square plus x plus 1 is clearly irreducible because it is degree 2 and it has no root in Z5, so it is irreducible in Z5x, and since Z5 is field, so Z5x is Euclidean domain. We need only PID here, so it is also PID. So the ideal generated by this polynomial is maximal here. So this ideal is maximal in Z5x, and hence this quotient ring Z5x by this ideal generated by this is a field. So this left hand, the ring in here, which is in left side, Zx by the ideal generated by this x square plus x plus 1, this is also a field because these two are isomorphic rings. So since this quotient ring is field, so this ideal which is generated by 5 and x square plus x plus 1 is maximal ideal. So this is a maximal ideal in Zx. Now look at here, this ideal is our J, and we already have J is contained in I, and I is also a proper ideal. So we must have this J equal to our I, because if I properly contains J, then J cannot be a maximal ideal. So also I is a proper ideal. I is not equal to Zx, so we must have J equal to I. So now these two ideals are same. So now these two ideals are same, J equal to I. So here our Zx, so as our J equal to I, so our these two ideal Zx by J is actually equal to Zx by I. This is our given quotient ring. So our Zx by J is a field. So this Zx by I is a field. So since it is a field, it is also an integral domain. So in options, option 1 and option 3 are correct because this Zx by I is field. So it is also an integral domain. So here option 1 is the correct option. This ring is denoted by A, so A is an integral domain and also is a field. Option 1 and 3 are correct option. Now see, since it is a field, so it cannot be a product of rings, because a product of two rings always contains divisor of 0, but a field cannot contain divisor of 0. So option 4 is not the correct option. So option 4 is not the correct option. So we need only to check option 2, it is a finite ring or not. Now see, this ring is actually our Zx, that is A equal to our Zx by I, that is equal to our Zx by J. J means the ideal generated by 5 comma x square plus x plus 1. We have denoted this ideal as J. So also we have this is isomorphic to Z5x by the ideal generated by x square plus x plus 1. See, a ring ZPX by an ideal generated by some polynomial fx, where this fx is a polynomial in ZPX of degree n. This ring contains p to the power n elements. This is very easy to verify, because if we take an element, say phi x from here, phi x plus this phi x plus this ideal from here, then see, uh, if we divide this phi x by fx uh, by division algorithm, so we have a quotient polynomial qx and remainder polynomial rx, and we have this degree of rx is either this is 0 less than equal to this and less than degree uh, fx, and which is equal to n. So clearly this rx is a polynomial of degree at most n minus 1, and this phi x is of the form, this is fx into qx plus rx, this plus this ideal generated by fx, and this can be written also this fx into qx plus this ideal generated by this plus this rx plus this ideal generated by this fx. So this is also can be written, since this fx belongs to this ideal, so this is actually 0 plus fx, so it is actually our rx plus this ideal generated by fx. So now this rx is a polynomial of degree at most n minus 1, so this is of the form say a0 plus a1 x dot dot a n minus 1 x to the power n minus 1, and this all such ai are from zp. So there are p possibility for a0, there are p possibility for a1, and there are p possibilities for a n minus 1. So there are p into up to n minus 1 up to n times, because from this constant term to n minus 1 there are n possibilities, so p to the power n. So this rx are this p to the power n times, so such rx may be p to the power n. So any polynomial of from this ring zpx by this ideal generated by fx, so a degree fx equal to n is of the form where such rx may be this. So there are p to the power n elements. So in this case our ring a, our quotient ring a equal to our, which is isomorphic to zpx by this ideal generated by x square plus x plus 1. So this is a degree a 2 degree polynomial, and p is 5 here, so p to the power n, that is 25 elements. So this ring contains 25 elements, so this is a finite ring. So this ring is a finite ring. So option 1, 2, 3 are the correct options. So this is the solution of this problem. Thanks for watching.